So, Janowski and colleagues then provided evidence that there is regulation of the TRP operon after transcription initiation at the promoter region. And the region that is targeted by this regulation is the TRP-L or TRP leader region. Okay, so it's this region here. So if you delete the TRP-L region, this is an attenuated region, now you will eliminate this type of regulation that senses the concentration of TRP. So if you have double mutants in which you delete both this region plus the repressor shown here in a ribbon model, you bound to DNA, the DNA shown here as a stick model, and this is a dimer. If you delete the repressor and this region, now you do observe constitutive expression all the time, regardless of whether there is tryptophan or not. Okay? So it is more complex, and there is something else going on here.
Oh, question.
Now, deletions of TRP-L, pardon me? If I had a question? Yes.
This is Johan. So I was wondering.
Yeah.
So I was wondering if both of these genes need to be knocked out for constitutive or just the TRP.
TRP-L is not you are going to see in a moment, but what is the question?
So does TRP-L and TRP-R both need to be knocked out for constitutive or just one?
You have to have constitutive expression, you have to have both of them.
Both of them, okay. Thank you.
Because if you have you do not have the TRP-L, but you have a repressor and tryptophan, it still is going to be able to bind to the operator and block RNA polymerase from binding.
And if no, then
you do not have this mode of regulation, that I'm going to describe in a moment, but you still have the above that, you're going to have the repressor binding the operators and blocking transcription if there is tryptophan. If there is no tryptophan, then you're going to have expression. Remember, the repressor needs tryptophan to be able to repress. This is opposite of what is observed in lack operon.
Got it. Thank you.
Okay? Mm-hmm. Okay, so deletions of TRP-L are cis-acting. They do not act in trans, only in cis. And the transcription terminates in the leader region because of an excess of amino-acylated tRNA, as we will see in a moment. So this sounds strange, but we'll see in a moment. Okay. Now, this type of the regulation exerted on the leader sequence and the attenuator, because it reduces or regulates the level of transcription, was called transcription attenuation. Okay, and so let's look at how this regulation works. So this type of regulation is exerted after RNA polymerase begins transcribing or has exited the promoter. So remember, you have the promoter, you have the leader sequence attenuator. So it's after it has escaped the promoter. Okay, and so attenuation, transcription begins at the promoter, but terminates in the leader region of the transcript before RNA polymerase reaches the first structural gene of the operon. Okay, let me see. So transcription will, during attenuation, transcription will start here in the promoter and will terminate in this region before the first structural gene, depending on the concentration of amino-acylated tRNA trip.
Dr. Banuet, this is Alexis. I was just curious. So it terminates at the TRPE or at the end of the attenuator?
No, this is the structural genes, as it says here. These are the structural genes. It says it terminates before this gene. Transcription, during attenuation, transcription will terminate here in this region if tryptophan is high. And that is because you are going to have a lot of amino-acylated tRNA trip. Okay, so let me...
Thank you.
So, transcription attenuation is going to act by effects on RNA secondary structure. RNA, as you read and had assigned reading of this during the transcription chapter, forms all kinds of secondary structures. And these secondary structures play a major role here. Okay, so let's expand this region of the leader sequence. So you have the promoter, you start the transcription, and then you have the leader sequence attenuator, this here, and there are 4 different regions called 1, 2, 3, and 4. And here is where the structural genes start. Trp will start there, downstream. Okay, so in the first one, you have a start codon, AUG, and you have somewhere downstream of these 2 trip codons, UGG, UGG. Okay, and then you have a terminator for translation, okay, UGA. Nonsense codon, not a terminator for transcription, but a termination for translation. There is going to be a transcription terminator involved here. Okay, so according to the model that I'm going to describe, it is the concentration of amino-acylated tRNA which determines what type of secondary structures are going to be formed in this leader RNA sequence. Okay? So let me, instead of saying that in words, let me just put it here in the diagram. So you have this. You can form these hairpins. So one can form a hairpin with 2. This is normally formed. This is called a pose hairpin. And then you can form 3 and 4. So you form 1 and 2, you can form 3 and 4. And this is a typical terminator helix. In other words, if RNA polymerase encounters this, follow, by this string of views, it's going to terminate, it's going to fall off. And this happens when you have a lot of tryptophan. So you do not need to transcribe the structural genes if you have all this tryptophan. So this secondary structure is induced by the presence of a lot of tryptophan. Now, the alternative is that you form 2 and 3, okay? 2 and 3, which is an anti-terminator hairpin, which allows RNA polymerase to continue transcribing into the structural genes. This is because you have no or very little tryptophan. So when the ribosome is translating this region, it will come to the UGG. It will have to, the codons will have to be recognized by tRNA trip to insert the trip. But if you don't have trip, that causes the ribosome to stall here and allow the formation of this hairpin, which is a signal for RNA polymerase to continue transcription. Okay, we are going to look at this in more detail. So the important thing to keep in mind is that you can form these alternative secondary structures. If you form 3 and 4, bingo, that's a signal that RNA polymerase cannot continue. If you have 2 and 3, that's a signal that RNA polymerase, I should say, RNA polymerase, should continue and transcribe the genes that make the enzymes that convert choriamic acid into tryptophan. Okay. So, there are too many words. Let's just go and look at this diagram. Okay, so I do have this here. Okay, so let me exit. Okay, yeah, that's what I want. Okay, so here we have RNA polymerase has started the transcription process at +1 into the Trp-L region. You have to remember that in bacteria, this is not true for eukaryotes, in bacteria, transcription and translation are coupled. Here is, I think it's coming out. Okay, transcription and translation, this is RNA polymerase are coupled, so RNA polymerase, and here you have the ribosome behind the RNA polymerase. Okay, so let's see what is happening here. You have that RNA polymerase started transcribing, okay, and now here you have region 1 and 2, so RNA polymerase transcribes 1 and 2, okay, so it's sitting here past the end of region 2. 1 and 2 form this hairpin. Here you have the UGG, which are the two tandem tryptophan codons. Behind, so when RNA polymerase forms this, or not RNA polymerase, so RNA polymerase transcribes 1 and 2, this hairpin forms, and signals RNA polymerase to pause. It's going to pause momentarily. Behind it comes the ribosome. Okay, you have an AUG, and it starts translating, and so it kind of bumps. So the model is that it may bump into the RNA polymerase, push the RNA polymerase to continue transcription, and if there is abundant tryptophan, then you're going to have the ribosome encounter this translation termination signal. What is happening to the RNA polymerase? Okay, so let's look in the presence and absence of tryptophan. So if you have lots of tryptophan, you have lots of tRNA trip, so the RNA polymerase continues the transcribing, because remember, pausing by RNA polymerase is only very brief, so it is going to continue transcribing into regions 3 and 4, so it transcribes region 3 and 4. You form this hairpin with this set of U's, a string of U's, and that is a signal of termination of transcription. Transcription termination. The RNA polymerase falls off, and then the ribosome has, inserted tryptophan here, but it has a stop. When you have a stop, you have release factors. The ribosome falls off. No RNA polymerase, no further transcription, no further translation. That's it. Okay, so you stop with tryptophan. Okay, so without tryptophan, we have that, again, polymerase that transcribing forms the region behind it comes the ribosome and encounters, remember the codons, trip codons are here, the RNA polymerase pauses momentarily, then the ribosome encounters the trip codons, it tries to insert the tryptophan, but there is no tryptophan, there is no or very little tRNA. Trip, okay? In the meantime, RNA, because the ribosome now is stalled here in region 1, so now RNA polymerase continues transcription. Region 2 is going to be free to form region 3. The ribosome is tying up region 1 now. And then this is a signal for RNA polymerase to continue transcription and synthesize the structural genes. So again, when the ribosome encounters one of the UGG codons, it will stall, it stops because it's unable to insert trip. And this stalling sends a signal that the trip concentration is low and that transcription should continue. And how is that signal sent? Via formation of the hairpin 2 and 3. Okay? So again, this is because transcription and transfer in bacteria. As soon as you have a message exiting RNA polymerase, the mRNA exiting the RNA polymerase, remember there is a channel for exiting, the ribosome immediately binds to that, the ribosome binding site on that message and starts translation. Okay, so this is from your book. I suggest that you read very carefully this section in this book. This book has really very clear writing. The people that wrote this book are microbiologists. That's what they teach all the time, this stuff. And this